you for the introduction and thank you for inviting me to the organizers to the conference. Can you hear me all right? And can you see my PowerPoint?
Yes, perfectly.
All right. Okay, so it's a little change of pace and topic. There are so many fantastic things to talk around about in the context of photonics and photon science in general. I could also give a very applied talk about some remote sensing technology that we have been developing, but I guess for this presentation, I'll focus on a different topic. So I'll talk about X-ray scattering, which is a little different theme, but I'll try to bring you through a fascinating story that has been developing over the recent years. All right, so before I get going, I great number deeply indebted to my collaborator, Mike Miniti, who's at and the University of Edinburgh, in particular, Professor Adam Carrender, who's been a long-time collaborator with me on this project and a brilliant theorist. And then finally, a large number of students, graduate students in my research group, many of whom have now graduated and moved on to do different and new things. And then finally, also, I collaborate very closely with my friends and collaborators in Nebraska, and, Kansas State, and Louisiana, and so everybody deserves some attention, in particular also the funding agencies who've been generously sponsoring this research. So here's the outline of what I'll tell you about a little bit, and each of the parts has to be short by necessity, but I'll give you and what kind of chemistry we seek to understand. I'll talk about spectroscopy and scattering experiments in general, but then a little bit more in detail about X-ray scattering. I'll tell you about the fantastic facilities that now exist for X-ray work, and go a bit more into the depth of scattering theory, although not too much, but somewhat. And then I keep the last part short. These are actually the achievements that we've made over the last decade. And I'll just give you a flavor of some of the very many things that we have been able to uncover. Chemists, and I'd like to understand chemistry. Chemistry is always about the transformation of molecules from something to something or else. And so chemical reactions are very essential, key. If you want to understand chemistry, you need to understand chemical reaction. Now, when you take chemistry, and many of you have taken chemistry as students, the level of depth in chemistry is bafflingly shallow. And so here is my cover of my old book from Woodward and Hoffman, and they received the Nobel Prize on their work 50 years ago, 60 years ago almost, and it talks about chemical reactions in the terms of orbitals, little orbitals that are blue or green, and they align in certain ways and rotate in various ways. And that's clearly a very simplistic description. It has its merits in the sense that one can use it to plan some chemical synthesis, and then one hopes it works, and sometimes it does, sometimes it doesn't. Like this book by, it's the same description about how chemical reactions work, and it is not any more deep than it was in the 20th century. So traditionally, what happens is that chemists only look at what molecules go into your reaction and what molecules come out, and they draw inferences about what happens. And that these inferences, they are sort of embodied in hand-waving rules, such as these rules of orbital symmetry by Woodward and Hoffman. Ultimately, we need a much deeper understanding, because we know now that these reactions, these here that I draw on the right, are very complex reactions that involve absorption to an excited state. There is a conical intersection here, it gets bypassed, and the state here this doubly excited state gets prepared. That's actually the Woodward-Hoffman state, but then it reacts in an off-symmetry fashion to either create the product or not. And so the chemical reaction is much more complicated. If we want to understand chemistry, if we want to predict new chemistry, we need to know these kinds of details. So what holds us back from such a deeper understanding? Ultimately, we need to see better how molecules react. We ideally would like to have a molecular movie, something that I can look at and say, this is how the reaction proceeded. And ideally, I'd like to see the nuclei, the atoms of the molecule move. I'd like to see electrons move. That's what I ideally like to have. So that's what we're setting out to do. The movies, once I create them, could then lead to further theory calculations, and that then could be to a broad implication into the 21st century chemistry, as I hope. Okay, so our research goal is to look at nuclear dynamics, the transformation of molecules, and electron dynamics, the chemical bonding, and to watch them both in time and in space. And typical time constants are in the, let's say, tens of femtoseconds time range and in milliangstrom spatial distances. And so the challenge, the challenge is to devise technologies and techniques that allow you to look at molecules on these kinds of time and length scales. Okay, so I've been many years ago. So we have done a lot of techniques, and so over the years we developed photoelectron spectroscopy as a way to look at chemical reaction. I've done a great deal of work on electron scattering that I also started back many years ago. But I'll tell you today about X-ray scattering, which has been particularly dear to my heart in the last few years. And so off we go with X-ray scattering. And I should tell you that we do our experiments on molecules in the gas phase for many reasons. And they're shown in this blue box. And in particular, there is very good theory to compare your experiments to. And that's even though the random orientation of the molecule washes out some specificity, it is so that the randomness of the orientation of molecules in the gas phase is pretty darn near perfect. And so we get very, very good advantages. There is no sample heating. We can avoid sample damage, and I'll tell you about that in a little bit too. There are drawbacks, and one of the drawbacks for X-ray scattering is that the cross sections are small for X-ray scattering, and also, as I mentioned, the random orientation does lose you a little bit of information. And then some things are just different than in crystalline phases, and so in X-ray scattering in the gas phase, we look at the total scattering, and I'll explain what I mean with that in a little bit. All right, so first of all, if you were to have one molecule that's sort of clamped, fixed in space, then it might give you a scattering pattern as the one shown to the left. And that does have a great deal of information about the molecular structure. The formula is shown here. Essentially, the scattering signal that you measure is the Fourier transform of your molecular structure. The R is the interatomic distances. That's what you really like to have. And so the scattering signal is the Fourier transform of that. When you look at a gas phase scattering, because of the random orientation, you lose some of that. However, you see that the scattering signal, the sigma, your scattering cross section as a function of scattering vector, is now still very clearly given by a transform. It's now a sign transform. And so again, you can use an analysis of these kinds of patterns to get the molecular structure. So just because the molecules have random orientations in the gas phase does not kill all your information content. Okay, so to do a gas phase X-ray scattering, what we do, we want to measure molecules that are reacting. You first excite the molecule to an excited state that now starts the chemical reaction. We use a laser pulse to do that. It's a short pulse laser, and typically we use something like 50 femtosecond pulse duration with wavelengths between 200 and 260 nanometers, let's say, in the UV range where photons can induce chemistry very well. And then a little later, a few femtoseconds later, we come with our X-ray probe pulse, and we now scatter the X-ray probe pulse, and we look at the scattering pattern, and we do that as a function of timing between those two. Okay, there are questions about the polarization. X-rays are polarized. I just skipped that. I mentioned to you earlier that we now do X-ray scattering, but many years ago we did electron scattering. The reason why we started with electron scattering is shown here. This is a log plot, and it shows the probability that one X-ray photon or one electron would scatter off one molecule. And you see the probability is very small. Of course, you do the experiments with many photons and many electrons, but so the probability is very small. But importantly, for electron scattering, these colorful curves up here, they're many, many orders larger than for X-ray scattering. So the X-ray scattering cross-section is very, very weak. Electron scattering cross-sections are quite large. And so it wasn't natural for us in the 1990s to start out with electron scattering. However, the game has changed a little bit, and the cross-sections are still small. However, we have great news sources. And so here's a picture of the LCLS, the Linear Coherent Light Source at SLAC National Laboratory. Let's see, here's a little aerial photograph. So you see it's at the end of Stanford's Linear Accelerator. This here is the freeway that goes to San Jose down in the bottom and to San Francisco high on the top. And so you see this accelerator goes clear underneath the freeway and goes right here. And if you just was going another half mile, then you would be down in the Stanford University campus, but the beam stops here. And so when we do our experiments, well, so here this bottom picture gives you an indication of where these electron and X-ray beams travel. They travel down this very long vacuum tube, essentially. And our experiment sits at the very end here. Our sample cell is measured in volumes that are sub-millimeter size, micrometer size. And so amazingly enough, this huge, long facility ends in our experiment focusing the X-ray beam to 30 micrometer where we use them. This is a fantastic light source. It is the best in the world. There are others that have been developed in the meantime, but LCLS remains. It was the first of its kind, and it remains the best of its kind. So currently we're using the beam at 120 Hertz repetition rate with photon energies of between 10 and 20 kilovolts, although that is being expanded now too. The pulse energy is in the millijoule level, and so at 120 Hertz, and pulse durations are less than 20 femtoseconds, so extremely short and extremely intense pulses coming at a high repetition rate. At the latest upgrade, these repetition rates will go up into, and you get even more photons delivered. Now, one of the things is that it can tightly focus these X-rays. And so, for example, if you focus these 2 millijoules, X-rays being very far in the blue, you can focus them very well. So if you focus them easily to a 1 micrometer spot size, then you get 10 to the 19 watts per square centimeter, a huge laser intensity, certainly huge compared to what I can generate in my optical lab at Brown University. And so we don't try to focus that hard, but it's, you can certainly access new regimes of optical intensity that you couldn't otherwise. It took us a little while. It took us a little while to harness the fantastic abilities of this instrument. And with a little while, I mean, you have to apply for beam time, and then you get typically 60 hours of beam time, and then you can do your experiment, and the first ones don't work because something or else doesn't go quite right. Then you try again, and maybe a year later you can give it another shot. So after some iterations, we now get to the point where we can get exceptionally high quality scattering signals. And so here is for a little gas, you see we keep it a very low pressure, and the sample cell length is 2 millimeter, and the X-ray beam diameter is about 30 micrometer. You see we get a huge signal from this small amount of gas, much higher than the background, and it's very clean, very beautiful. So it's really fantastic. Here's another pattern. This one shows the polarization of the X-rays. You get more signal in one plane versus the other, depending on the scattering geometry. So we get very high quality scattering pattern. Now, when you take this pattern, this is averaged over many shots. We typically accumulate for 10,000 shots, which doesn't take very long at 120 hertz. But, so we take many scattering pattern, you see a signal like that. If you just look at one shot, then you see how the photons are scattered. So incident here on the detector is are all these X-ray photons. Each little dot that you see is how a photon hit the detector. And so typically in an X-ray shot with 10 to the 12 photons, we get about 50,000 scattered photons. Okay, so let's think a little bit about this. Here's what happens. First of all, we're clearly looking at the particle wave duality. The X-rays, they're electromagnetic waves. They scatter like waves from your molecule. But then, of course, they're detected as particles, and that's not entirely unexpected, of course. The momentum geometry looks like this. You have an incoming photon here. Here is maybe sits your molecule. The incident photon moves on, but there is a scattered wave here that goes off to a scattered direction. Maybe here it detects your photon. The momentum transfer vector is this vector. It's the difference between the incident and the scattered photon. It's that red vector. And by conservation of momentum, your electron here that scatters the X-ray, that electron gets the counter momentum, and so that green momentum goes off in the opposite direction, but with equal magnitude. And so we have a process where, as the electron scatters the photon, it acquires a momentum in the opposite direction. Okay, so that raises a little bit of a conundrum that may not be unfamiliar if you're into this part of photonics. The X-ray photon hits the molecules and it scatters, first of all, as a spherical wave. Then it hits the detector, and that may take some 300 picoseconds to do. And that's, from the molecule perspective, is a very long time. But even though that is such a long time, that determines the Q vector of the electron. So it coalesces the wave function after 300 picoseconds, and that sort of reaches back in time, if you wish, to determine the K vector or the Q vector of the electron. So this might remind you of the Einstein-Rosen-Podolsky paradox, where Alice and Bob are observing the spins of particles. You have a source that generates two particles with opposite spin, and Alice sees one of them and Bob sees the other one. And so what happens is that when Alice here measures her spin in up or down direction, that determines Bob's spin without him actually needing to observe it in any which way. And so Einstein kind of developed that thought and brought it to the paradox. And it is vexing because if Bob now would decide to measure the spin in some other direction, let's say the X direction, then both the spin in Z and X direction would be determined, but quantum mechanically that is not possible to do. And another thing that, of course, in particular bothered Einstein is that Alice could be very, very far away. And so she measures the spin, and the information would have to travel infinitely fast. So it's a vexing situation, but ultimately it is so that the photon momentum and the electron momentum are coupled, and measurement of one gives you the other. And the reason ultimately, as is the reason for the Einstein-Podolsky-Rosen paradox, is that the two spins here in this example are entangled, and it's not that there is one spin and then another spin. It is that there is one system containing of two spin particles, and measurement of one determines the other. And just the same, for us, the photon and the electron are an entangled system, and measurement of one determines the other. Okay, so now let's see how that then works on the molecule basis. So you have, again, you have your incoming momentum and your scattered momentum. Your momentum transfer here is an electron. It acquires some kinetic energy and gets scattered. So quantum mechanically, you describe this with a scattering operator, which is the summation over all electrons in your molecule, and then e to the IQR. R is the position of the electron, and Q the scattering vector. For elastic scattering, you describe the signal as the square of these matrix elements, your molecule in the initial state, and you sandwich your scattering operator in between. Now, it can happen that your scattering process also excites the molecule to an excited state. Then that would lead to inelastic scattering. And then your final state here would be a little different from the initial state. Okay, so we look at the total scattering in our experiment, and that means that we look at both elastic scattering and inelastic scattering. And that is so because we don't have a detector that tells us if a photon lost a little bit of energy to the molecule or not. So we measure all scattering. And so now if you add up all your inelastic scattering factors, then you can invoke the completeness relationship to get this result here. Okay, so in principle, what we measure is very straightforward. We measure the total scattering here, and it is the expectation value of the sum over all your electrons, the scattering vector, and the position vector between the electrons. And in principle, you think this is straightforward, and in many ways it is, but in practice, there are challenges. And one of them is the following. So here, the elastic scattering, this here is a so-called a one particle property. It depends on the scattering operator, which has the position of your one electron in here. The total scattering here is a two particle property. It depends on the separation between two particles, the Rj minus Rk. And so fundamentally, you measure something else. So this already vexed Larry Bartell, who a brilliant scientist, who in 1964 already recognized that there are issues that arise from that, that relate to the correlation between your different electron positions. And so let me explain what happens. In a molecule, you have, if you have a molecule with n atoms, there are n, one half times n minus 1 interatomic distances that you can determine or that you can measure, but there are only 3n minus 6 degrees of freedom. And so if your molecule has 10 atoms or so, then the number of interatomic distances greatly exceeds the degrees of freedom that your system has. And so you always measure something overdetermined. All these distances are correlated. Now that leads to complications in the analysis. There are other complications that come in from unharmonicities. So here is, for example, a very unharmonic potential. And so that gives rise to complexities and bond shrink. So to make it long story short, we learned how to deal with all of these things and how to understand them. And in the meantime, now we have a agreement between the experimental data, the circles here, and the theory in total and elastic scattering that is really, really remarkable. So we can quantitatively measure scattering signals of even large molecules and interpret them to the point where we can challenge the quantum theory of molecules and the quantum description of molecules and contribute to truly measuring how electron density distributions are. Okay, maybe I'll skip this here about the radiation damage because I see that time is moving on. And let me just tell you a few stories of how we milestone paper in this field has led to a lot of follow-on work by not only us, by many other groups. And so what we were able to do is to determine these molecular trajectories, basically the molecular movie, where molecules move, and we can watch them by determining their structure. So this was our first shot. You see there are some trajectories that open up the ring, such as these on top. Other trajectories bring the molecule back down to the ring close form. So there are both ring opening reactions and ring closing reactions happening here. Okay, so skipping again some of the follow-on work here. I'd like to show you a bit more how we evolved this molecular movie. So this is this N-methylmorpholine system, a molecule that we also know quite well from our spectroscopy experiment at Brown University. When you excite that, this is a tertiary amine group. It tends to be pyramidal in the ground state, but when you hit it with a laser photon, it wants to be planar. And so this metal group starts to swing back and forth. And spectroscopically, that becomes manifest by these oscillations in the spectra that we measure. So going to SLAG National Laboratory and measuring that, we got a great deal of data, and we had to learn a great deal about how to analyze the data. So typically in a run, so we take data at 120 hertz. At each shot, we take a image with this large area detector. It's about a 2 megabyte image, and we read that out at 120 hertz. We, after a few hours of experiment, we walk out of there with about 100 terabyte of data. And now we need to learn how to analyze that, how to boil that down into these molecular structures. We devised methodologies that where we randomly create large pools of structures and theoretically calculate the expected scattering pattern for each of them. And then we compare with the experimental results, and we pick out of millions of structures, the experiment picks the one that most closely seems right. So that procedure, it also includes correction, and in particular the electronic correction. When the molecule gets excited to an excited state, then the scattering signal changes because the electron density distributions change. And so we had to learn how to account for that. And once we have done all that, we actually do get our structures. So here is a table of structures that we can measure in this molecule. We get the complete molecular structure with very good precision. And I don't have time to go into this. But we do this in different ways, and we see very good agreement between the methods and between the computational results if you were to compute it. And so we have a robust experimental method to determine the molecular structures. We need to include the electronic excitation corrections, and it is important to have a sufficiently expansive and dense structural pool to obtain really high quality structures. And so with that, we now can give you the molecular structures as a function of time. So this is just an excerpt of a long table. Here's time in femtoseconds, not picoseconds. So it's 50 femtosecond time steps. Each row is another 50 femtoseconds. And then we have all these atom distances for the entire molecule. And so we can watch how first change, and we can assemble it into a little movie like the one that is shown here on bottom. We can make plots of how the bond angles change, how carbon-oxygen distance may change. And we may also see that some parameters don't change. They're clearly not affected by the optical excitation. Okay, so maybe I kind of leave it at this. What we have achieved is to measure these time-dependent molecular structures, which has been a dream for many years. When you think about it, for about 100 years, chemists have measured molecular structures in the ground state, and all knowledge of all chemical structures are based on such ground state measurements. Chemistry is specifically about the transformation of molecules from one state to another. And so ideally, you would like to watch the structures of molecules as they evolve from one side to another of your chemical reaction. And for the first time, about 100 years after the ground state structures, for the first time, we are now able to truly measure chemical structures of molecules while they react. And so I could tell you many more examples, but as I said, we'll skip them. And thank you very much for your attention. Be happy to take some questions if you have any.